Alright, so in the previous segment, we walked through the algorithm for deadlock detection when you have multiple instances of a resource type. So I'm going to dive into the examples straight away in this segment, and then we will also look at the interpretation of the algorithm. So if you are not familiar with the algorithm, I would encourage you to revisit the previous segment, make yourself familiar with that, and then come back here. Alright, so we are going to take a system with 5 threads T0 to T4. Threads and processes are the same, and 3 resource types A, B, C. So we have 7 instances of A, 2 instances of B, and 6 instances of C. So this is your initial condition. So allocation, request, available. Again, I explained to some extent the meaning of all these terminology in the previous segment. So if any of you have a doubt in any of these terms, I would strongly recommend that you go back, revisit that segment, be very familiar with what I've talked about there, and then come back here. So I will not spend too much time here talking about what these various terms mean, right? So allocation, so T0 has claimed so far 0 instances of A, 1 instance of B, 0 instances of C. T2 has claimed 3 instances of A, no instance of B, and 3 instances of C, so on and so forth. Request, for example, T1 is asking for 2 instances of A and 2 instances of C, nothing in B, so on and so forth. Now, out of these 7, 2 and 6 instances of A, B and C respectively that the system has, everything has been allocated somewhere, nothing is available right now. So if you look at the allocated values for A, 2 plus 3 plus 2 adds up to a 7. For B, 1 plus 1, I'm performing column wise addition in case you're not able to make out, that adds up to 2. And for C, 3 plus 1 plus 2, which is 6. Yeah. So if you see, whatever has been allocated for C totally adds up to whatever amount of C we had. Similarly for A and B, which is why available is 0. This is our initial data given to us. Now, the algorithm said initialize work equals available. Available is a 0, 0, 0. So I'm initializing work 0, 0, 0. Finish, it said, again is an array, length equal to the number of processes. If any process has allocation equal to the 0 vector, then for that process finish must be true, or else finish must be false. Clearly, nobody has a 0 vector under its allocation, so finish equals false for all 5 threads or processes. So that is our initial condition. We start. So the algorithm said find a process such that finish is false and request less than equal to work. So I'll start with T0. Finish for the 0th index is false and request is 0, 0, 0, which is less than equal to 0, 0, 0. So I'm sorry, this needs to be request less than equal to work. I apologize, I will correct it. If you remember from the algorithm, it must be request less than equal to work. Alright, this is a PDF. I will update that later, but yeah, I apologize for this mistake. This needs to be request less than equal to work. And yeah, request here is 0, 0, 0, which is less than equal to 0, 0, 0. Finish of 0 is also false. So T1 qualifies for what we're looking for. So what do? You allocate request, T0 qualifies. So you allocate whatever T0 is asking for, you finish working on it. Now what happens is, what this basically means is, T0 has this much allocated, it has not been finished yet. Now it is asking for something, and that something is within the bounds of what we can afford to provide. So you provide that something, you make T0 finish its work, and then you take away everything that T0 has. In this case, you don't need to provide anything because the request is 0, 0, 0. So you make T0 do its work, and then you take away whatever T0 has and you add it to your work. Work is basically like your inventory, where you keep stock of what is available with you. Work and available are one and the same actually. So right now T0 is requesting for nothing. So well and good, ask T0 to work. Once T0 has finished, this 0, 1, 0 will be returned by T0, and so that comes and adds to your work. So if you remember when we discussed the algorithm, in the step 3, the update was work equals work plus allocation I. I apologize if there was any background noise. Yeah, so work equals work plus allocation I. So work is 0, 0, 0 plus allocation of the chosen process is 0, 1, 0. So your work gets updated to 0, 0, 0 plus 0, 1, 0, which is 0, 1, 0. And you set finish of that process to true. And you finished with that process, so you strike it out of the list. Cool. Now again we proceed. Now your work is equal to 0, 1, 0. Your finish looks like this. You have 4 threads remaining. Start. So for T1, finished is false, but request is not less than equal to work. You have a 2, 0, 2 here, and this is a 0, 1, 0. So what do I mean by less than equal to here? By the way, I'm comparing arrays, right? So I'm comparing arrays element wise. So every element of request should be less than equal to the corresponding element of work. That is what I mean by request less than equal to work. So if you see, T1 is requesting for 2 units of A, but what I have right now in my inventory is 0 units of A. So I cannot accommodate T1's request at this instance. Probably later, yes, but right now, no. So I will not deal with T1 right now. I'll move to T2. For T2, finished again is false. Request is 0, 0, 0, which I can afford within the bounds of what I have. So I will allocate to T2. I will let T2 work, and then I will claim back what T2 has. So allocation again, there is no request, so I'm not providing anything extra. I'll ask this fellow to do what it wants to do, and then this 303, I will take it back. So once that is done, if you see here, T2 has also finished. So I had this in my inventory. Now this fellow finished and he's returning his resources to me. So 010 plus 303 becomes 313. So again I repeat, I've just written this down in this format for illustration purpose, but these are not 3-digit numbers. It is an array or a vector with 3 separate units, and we do element wise addition, right? So I have 3 instances of type A, 1 of type B, 3 of type C. And again, of course, in my finished, in the position number 2, I make it a true, right? So that again, that's what the algorithm said. Now you move on. Again, T3, finished is a false. Request 100, I can afford to provide that with what I have. So I will allocate this 100 over here. I will make it finish doing what it wants to do, and then I will take back what T3 has to offer, right? So yeah, that's what's happening. So you will allocate one instance of A, and then you will let T3 work, and then you will take back. So according to the algorithm, what we do is we strike this off the list. You had a 313 already. This person needed a 211. So that this person was allocated a 211. So you add that. Work is equal to work plus allocation. It becomes this, and at T3's position you make it a true. Now there is actually a small thing going on here behind the scenes, which I would like to just illustrate. So what happens is, in the previous 2 cases, request was nothing. So you weren't really giving anyone anything. You were just telling the respective process, you do you basically. Here you are allocating something. So what actually happens is, from your inventory you will be giving one instance of A to T3. So this 313 will become a 213, and this 211 will become a 311. So you are taking out one instance of A and giving it to this process. That process, so your A count will be decremented by 1, and that process's allocation will be incremented by 1. Then that process will work, then it will give back everything it has. But that thing we are not illustrating there, because ultimately you're going to get back everything that the process has, right? Everything it originally had, as well as everything you allocated newly. So that -1 + 1 thing just gets accounted for. So in order to not complicate things by adding one more step, we do not illustrate this becoming a 213, this becoming a 311, then that getting added. But if you check it out that way also, you take a 213 plus 311, that will also give you a 524. So that is, I just mentioned that point here in order to give you an idea of what is happening behind the scenes, which is when you have a request which you can afford to allocate, what you do is from your inventory you will allocate that much. So your inventory reduces by those many units, your process allocation increases by those many units. Ultimately everything that the process has is given back to you after completion, so that plus or minus makes no difference. So ultimately what you will do is inventory or work equals work plus allocation of I. So yeah, we get a 524, and corresponding to T3 we put a true. Next, proceeding T4, finished is a false, request is 002, which again I can afford to provide. So what I will do is, I will take 2 units of C, which is what this person is asking for, and give it to him. He will work and then he'll give it back to me. He'll also give everything else he has. So I have a 524 and it gets added with a 002. 524 plus 002 becomes a 526. Also this process has completed its execution. So I set finished equals true. So now I have only one process left. So moving on, fifth process, the last one. So again there is T1, finished is false for T1 if you see, and request is 202, which I can afford to provide with my existing inventory. So again I will allocate, T1 will finish, then T1 will give me back everything it needs. So 526 plus 200 is 726, and finished of T1 is equal to true. So now if you see, all processes have been completed. So finished becomes true, 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 which means it's the end of the loop, right? If you remember, in the loop you had to find a process such that finished is false and request less than equal to work. Now there is no process such that finish is false, so your loop ends. So it's the end of the algorithm. Now if you check, now the step 4 of the algorithm said, when your loop breaks, you check this array called finished. If everything is true, it means there is no deadlock. If something is false, it means there is a deadlock, right? So we check here, there is no false entry, everything is true, meaning all our activities happened to be executed smoothly, so there was no deadlock, right? So there are 1 or 2 things I would like to draw to your attention here. Firstly, finally after everything completed execution, if you look at your inventory, it is 7, 2, 6. 7 units of A, 2 units of B and 6 units of C, which is exactly what we had to start with. If you remember, the same snippet is what I showed you over here at the beginning. 7 instances, B has 2, C has 6. So what I'm trying to say is, once everyone has finished and once everyone returns their whatever they had claimed, you will have exactly what you had to begin with. That is one point I wanted to convey. The second point is, when you reach the end of the algorithm, or when your loop breaks, not the end of the algorithm, when your loop breaks, you check the finished and you see if everything is true, it means there is no deadlock. If something was false, it means there is a deadlock. So I'll be giving you an example for that case later and I'll be asking you to solve. But as of now, that's the theory part. So that is one thing. And another thing is, there is no deadlock because we executed these processes in this specific order: T0, T2, T3, T4, T1. 0, 2, 3, 4, 1. If you execute these processes in this sequence, there is no deadlock. Whereas if you go in some other sequence, let's say 0, 1, if you allocate to 1, either you will not be able to allocate at all because you don't have that much in your inventory, or if you are able to allocate, it is possible that you will end up in a deadlock, right? So basically what this algorithm is going to give you is, if there is a deadlock, it will tell you that there is a deadlock. If there is no deadlock, it will give you that sequence in which your processes need to be executed in order to run smoothly without any deadlock, and such a sequence is called a safe sequence. So when we look at deadlock avoidance, we will be looking at safe sequence, safe state in more detail. But for now, safe sequence is basically any order in which you have to execute processes, more like allocate resources and allow processes to run such that there is no deadlock. So yeah, that was the example. I'll quickly recap. So you had this data given, you initialized work is equal to available and finish is false for everything. We started with T0 and worked our way down to T4. At every step you looked for some process such that finish is false and request less than equal to work. Whenever you found a process, you basically from your inventory you gave it whatever it was requesting for, you made it run, and then whatever was there in allocation, everything you took back to your inventory. So because that giving is compensated by taking back, that give and take we are not, so for example, if I'm giving it 1 unit of A, that 1 unit is anyhow being returned back, so that's a -1 +1, so we do not depict that explicitly because it's implicitly understood. So whatever was already allocated, that is what is newly being returned, so that we depict by saying work equals work plus allocation. We set finished equals true for that job. We repeat until we are not able to find a job such that finished is false and request less than equal to work. When you reach that state, we check the finished array. If everything says true, it means this is a safe sequence. The sequence in which you allocated and executed is a safe sequence and there's no deadlock. If at least one of these values is a false, it means there is a deadlock. And if there is no deadlock, finally at the end, your inventory will be equal to what you had when you started out with. So that was an example. In the next segment, I'll give you a quick overview of what exactly this algorithm did and why we did what we did. Although I did explain that in this example, I'll formally put that in the next segment. Thank you.